If it is present in the cache, read it or write it and mark a flag dirty. But in both cases, first you are loading to, you are bringing to cache if it is not there in the cache. Store also does loading. Store brings it to cache. Let's not say store does loading. Let us say store loads the thing to cache. Store both load and store to main memory, to some address, involve bringing data to cache. If you want, let's call it as a load to cache. Okay. Once it comes to cache, you decide, it's a load, read it from cache, thank you very much. You're writing something, then you mark it a dirty bit. Once it is dirty, what happens? Correct. Let us say I have written to this element. This element I am writing. So to write, this cache line has come to my memory. I have written some new value. Let's call it as 5. I have written an old value or something. Let's say old value was 3. I have written now 5. I have marked it dirty. I have not written it back to the cache yet. When will I write to cache? When it is when the cache line has to be replaced. When will I replace the cache line? Let us say some other elements have to be brought in. Some other elements have to be brought in, then at some point I will run out of my cache and then this whole thing has to be written back. Correct? So what are the steps? Both load and store, bring it to cache, write if it is a store, read if it is a load. And in store, there is an additional thing. Whenever this cache line has to be evicted, you have to write it back. Are the steps clear? For store, maybe I have a if it is a write, there is a miss. If there is a miss, if there is no miss, well and good. If there is a miss, I will request the memory, give me a cache line for overwriting. I will tell the memory, this is request for overwriting. I will request the memory, boss, give me a cache line for overwriting. And then I will, so memory will do the loading. One full cache line, 0 to 7. And then I will modify and mark it as dirty. This is what happens for C0i. Okay. For what happens C1, I? C1, I, there is a cache miss. If I do not have space in the cache, I may even have to evict this C0 that was brought in. This eviction requires writing back, and then again you will do, hey, I want a new cache line for overwriting. Then again I will load that thing, again modify and dirty. There is a modify that's missing here, sorry. Am I making sense so far? What happens in a load? Let's quickly look at in a load. In a load, what happens? Did you miss? I will ask memory, hey, give me. Not for overwriting, just give me that line. I read, it comes to cache, I will use it. There is no dirty bit. There is no write back required. Yeah? And same thing for all memories, for all elements. Okay, that's what happens. Okay, let's get back to this. So here I have n square cache misses for write. Is that fine? What happens here? I have interchanged. Do you see that there is no dependence between iterations? Is there any dependence between iterations? No. I can interchange. This is safe to interchange. But is it profitable? You will see now I am going for each value of j different values of I. So fix a j, let us say j equal to 1. I am writing to j sub 0, j sub 1, j sub 2, j sub 3, j sub 4. I am writing in order. Correct? What about reads? Read now are having cache misses. Why? Because for j equal to 0, I am doing 0, 0, 1, 0, 2, 0, 3, 0, n, 0. Correct? So this is again like here. I am reading here. In the modified code, I am reading it. The read strides are distance of n. Isn't it? So this n distance, in the top code, the write distance was at a distance of n. Here the reads are at a distance of n. कुछ फर्क पड़ता है क्या? Okay, so one question, one suggestion is, hey, reads. Let's both are otherwise same, but reads are. She's saying for some reason I don't understand. She's saying, well, let's stick with the first one. And why is that so again? Same thing with store also. I mean, here there is no dependence. Why should it stall? There is no dependence here. No? Here there is no dependence. No? But here there is no dependence. I mean, the read, no one else, no other element depends on, no other iteration, no other instruction depends on a sub ij. Only I sub j depends. Any thoughts? Which will save some time. Nice. See what he is saying, look at this way. When I write an element, multiple things are happening in between. We just saw some steps, no? There is a miss, you bring it to cache, okay, then you modify, mark it dirty and then evict. Correct? Now let's see what happens. Let us say I follow this option. Which one will I first, let's write it. First I will write C sub 0, 0. What will I do? I will bring this line. This whole thing is in my memory, in my cache. All these 8 elements are in the cache. Then C comma 0 comma 1. What will happen? It's there in the cache. I'll mark it, it's already marked dirty. No issues. It will remain perfect. Same with 0 comma 1 to 0 comma 7. They are all cache hits. And importantly, I am not writing back. Previously, for this element, I had to write back. This element, I had to write back. This element, I had to write back. And when I am writing back, I am sending the full cache line. Now, for all of these together, I will have a single write back. For the cache line is sent back only once. Okay. So, if you want to count the time, right, in the original code, when the writes were happening, there was cost to evict, there is a cost to fetch with permission to overwrite, right? So as a result, for each cost per write, okay, there is cost for RFO, there is cost for modify and write back, okay. If this is around 300 cycles, bringing from memory to cache, there is some small cost, say around 100-150 cycles for eviction and write back, okay. So what's happening is that for you are not utilizing across writes, you are not utilizing the cache line. So for every write, you are paying the cost of modify write back, modify write back, okay. How many writes are there? N square writes. So if you multiply, so basically we are saying 1024 cross 1024 n square times 460 cycles for total writes. If the reads were misaligned, how much cost will we pay? Right? In the interchanged code, my writes are aligned, my reads are misaligned. What's the cost I will pay? It's a cache miss. I will do a load. I will do a load. No write back required. No modify and write back I don't require. As a result, in every miss, remember I will have n square misses for reads, but the cost at each point is only 300 cycles, only the load cost. So if it's a write miss, you will pay, cost is 460 cycles. If it's a read miss, it is 300 cycles. Both are n square. Both have to be multiplied by n square. So if you are encouraging write misses, you are paying 1.5 times extra cost compared to if you are encouraging read misses. Time, cost in terms of time. So, and on top of just this write misses, every time you are saying, hey, is marked as a dirty and write back, right? There is an cost of the L1 cache getting polluted. So L1 has to be, it keeps on thrashing. So the actual cost significantly changes to something around 10 to 15 times. So in the original code, the cost, the runtime could be, let's say, on a machine we tried, around 250 milliseconds. Interchange is 15 milliseconds. See, there can be a simpler code where if you interchange, in the original code, everything was going at a distance. I'll write a very small code for you. For I equal to 0, I less than n, I plus plus. For j equal to 0, j less than n, j plus plus. Let's say I am accessing a sub j comma I plus plus. Some simple code. Okay? A sub j comma I plus plus. If you interchange the loop, what will happen? So here, okay, how is the cache access here? Column wise, but my array is stored row wise. Lots of cache misses for reading and writing back. Yes or no? If you interchange the loop, all are very nicely aligned. In ours, the example we saw is more involved. Here, there are cache misses for writes. Here, there are cache misses for reads. Both are memory accesses. Both are memory accesses. Some are more costlier than other. all animals are created equal, some are more equal than the others. Okay, so here because of my interchange, because of my loop interchange, the writes became faster. The writes became faster, the loads became slightly slower, but comparatively overall the program is faster. Possible. So we are, see, Jayashri. So what Jayashri is saying, look, you are optimizing this code, what effect does it have on some other part of the program or some other program which is running in parallel could be. So that's going to be much more difficult to analyze. So what we will do most of the time for our discussion, we will keep it to, if I am compiling one code, I am assuming only that code is running, others are not. Okay? And yes, it is myopic in the sense we are not taking into consideration what other things may be running. But it's very difficult to know what other things may be running. And even within the same program, what effect it may have on some other part of the code. What if this is inside some other loop? Right? We are saying let's only focus on this. If you want to consider a bigger chunk, you need also more complicated techniques. Well, let's focus on these simple ones for the time being. But let's keep in mind, this is not panacea. Right? It can lead to, it can have effect somewhere else. Right? But if this is the code, here is a way. Correct? Go take a wash and come. Yeah. So what we are saying, so loop interchange can be very useful because of the effect on cache. Right? I mean, we are not, are we reducing any operations? Loop unrolling, we reduced operations. What operations did we reduce? Number of branches, not iteration, number of branches. The operations we have done it the same, but the branch instructions we reduced. Correct? Here, have we reduced any instruction? No. Have we changed the code size? No. No impact on code size. We are not changing actually any assembly code. If you look at the number of instructions, it's going to be the same. But one is more efficient than the other. Why? Because we have impacted the cache access patterns. Right? Check with your neighbor. Check with your neighbor and take few minutes and convince yourself that the modified code is more efficient than the code. Maybe what I will do, let me see if I can show all these things together. Oh, bad. Oh, I made it animation, is it? No, I'm sorry, I am not able to place it. Oh, I can. What the heck? Why I cannot? Okay, yeah, so you can see the cost of writes in one place and cost of reads. Yeah, so this is the cost of writes cost of reads. Take a look. So ऊपर वाले I can do it a single page. Yeah. Cost of writes, cost of reads. Okay. Uh, I hope you remember the original code. In the original code, you are writing to C sub ij. Okay. Chalo, take a look. Convince yourself that this is the interchange is effective. Neighbors time. Could be. I mean, at some point we have to evict them. Sure. I mean, whenever we evict, see what's happening is that by the reason why I'm saying evict here, I have 1024 columns. There's 1024 such writes. By the time I'm finishing, it's 1024 into cache line. I have probably much fewer cache lines that I can store in my L1 cache. So by the time my 1024 is over, my full L1 is full, has to be destroyed. So at some point I'm evicting, so I just added that, right? So if I look at it, okay, evict, so it's so many evicts, 1024 evicts. I can probably save some. I don't have to necessarily evict immediately, but I won't, I mean, yeah, it depends on the. Look at the cost of, I wish I could have shown the original. Okay, you stay here, you stay here. Okay, right. So you have original code, transformed code, and cost of writes and reads. Now you can talk to your friends. Not convincing. Oh, so in reading, I don't have to write back, Baba. I don't have to send it back. Eviction is not an issue. But writing it back is more, so that's why I said the cost is modify in reading. I don't have a problem throwing it away. But here, every time I'm evicting, I'm paying cost. In the half.
Yes, it is working, but for loop is the one which is not working. But I haven't added that to test case. There is some grammar error that I am getting. For int I equal to 0. Yeah, that's what I did.
If you have your laptop. Do you have your laptop? Please try that once. All right. How are things? Are your friends convinced? All of you? I mean, if your friends are convinced with that example, please convince here also. Even in such cases, loop interchange can be useful, right? So this is a sub j comma I. Done. What's your name? Sriyoshini. Vani. Vani and Sriyoshini. Are you guys fine? Both examples, that and that.
The other example we can also just switch ij in the access, right?
Yeah, I mean,
Yeah, it does the same.
yeah, it does the same. All right, let's do one thing. If your friend is not yet convinced, let me know. We'll convince them together. You two are fine? Still some discussion required? What's the point? What's the issue? Huh? Missing? Okay. Can you explain what's the issue? Go ahead. Hmm. We'll write one element. In the original code, we'll write this first element here, then write this element. We will write this element only after I finished one column. Correct. Hmm. Hmm. No, 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 no. I am writing to this element. See, in the original code, I am writing C sub 0, 0. We are starting with 0, I hope. Then C sub 1, 0. Then C sub 2, 0. So this, and so on. Let me put the thing back. Yeah. So if you look at it, I am accessing in the original code for a given value of I am accessing 0 comma I, 1 comma I, 2 comma I, 3 comma I. So I am kind of jumping at so the writes are at a distance of n. Here the reads are at a distance of n. Here the reads are all consecutive. Here the writes are consecutive. Is that fine? All right. If there are no further questions, we'll continue the discussion. All right. Let's look at one more optimization. We'll call it as loop fusion. Okay? Loop fusion. Maybe it should have been called loops fusion. fusion of loops. Okay. Let's say I have code like this: I equal to 0, I less than 100. Same loop header, another loop. By loop fusion, what I want to do, I'll say, hey, don't go over the loop twice. Because here I'll do 100 branches, here I'll do 100 branches. Let me fuse them together into a single loop. If I fuse them together, now I have reduced the number of branches by half. Number of increments by half. Yes or no? How many branches are here? 100 plus 1, the last one. Here 100 plus 1. Here I have 100 plus 1. How many increments I have? 100, 100, 200 increments. Here how many increments? 100. 100, not 1. 100. Even though the number is statically, it's yeah. So to do loop fusion, again I have to be careful. I cannot always do loop fusion just because these two are matching. Sorry? Yeah? Sorry. Yeah. So here, look at it. Is there dependence between them? Yes, there is a dependence. The second loop, iteration I, depends on previous loops computation in iteration I. In the previous loop, let us say I have written to a sub 2. That updated value should be used here. If I fuse, am I using the same updated value or the old value? I am in iteration I equal to 5, I am writing to a sub 5, then I am using a sub 5. Am I using the updated value like here, or am I using the an old value? Updated value. There is dependence. There is dependence. There is forward dependence. Okay. So there is dependence, but the same dependence is maintained here. I will state it in English. To compute C sub I, I need A sub I which was computed before or in the past. There is no issue with B. B and C, they are independent. So the only dependence is on A sub I. To compute C sub I need the value of A sub I which was computed before. In the transformed code, I am using the one that was computed. So these are equivalent. Do we have dependence? Yes. But this dependence does not stop us from fusing the loops. Teachers, if you, please feel free to come to the front. It will be easier to interact that way. Oh, okay. If you are planning to attend, then please come to the front. Yeah. We are fine so far? Okay. So fusion, what are the advantages when I fuse the loops? Less number of branches, less number of increments. Loads are parallelized. How? I won't say loads parallelization, but I'll say something similar though. Here let us say A sub I was not there in the cache. Let's say it's a very large number. You have to bring in so many things to cache, right? So by the time you finish, everything is cache evicted. So you got A sub I. You wrote to A sub I, wrote back A sub I plus 1, I plus 2, and finally again you are reading them. Here what's happening? You brought it to cache, from cache here, you wrote it, and then as a matter of fact, you will say, you know, another pass what it will do? It will write x equal to b sub I plus 1, c sub I equal to x times 2, a sub I equal to x. You won't even have two memory operations, you'll have a single memory operation. Instead of having one store and one more separate load, saying that, oh, it is in the cache, isn't it? See, let us say, in the most simplest sense, to load, to store, I must have brought it to cache, written it. I have a dirty block. When I am reading it, I'll read it from my cache. So this doesn't incur additional cache miss. But I am saying a compiler would do something much more smarter. It will write x equal to b sub I plus 1, c sub I equal to x times 2, a sub I equal to x. Oh, is it? Really? I forgot the time. Oh, so kind of you. Sure. After maybe 5 minutes. Thank you, madam. Appreciate it. You guys are hungry? I don't know. I mean, I forgot the time totally. Okay, but do you see what I'm doing? I'm writing x equal to b sub I plus 1, c sub I equal to x times 2, a sub I equal to x. What's the advantage? I have a single store, only one memory operation. This x could be put in a register for all you know, right? And I'm writing. So one store, the second load is gone. So the memory access has become better. Here I may have many more misses. Here I'll have misses for B, misses for A, misses for A, misses for C. Assuming if it is a large number, I will end up having 2n plus 2n, 4n misses. Here how many misses? 1, sorry, here 1, 2, 3, only 3n misses. Of course, in both the cases, you will not actually have n misses here, because once you are getting a sub I, in the cache line you will get the next ones free, but here it's much better, much fewer stores. I shouldn't have given that example, it has polluted your minds. Yes. So the impact of these optimizations on later passes is pretty difficult to gauge ahead of time. So there are works that try to do things together, multiple optimizations all done together. But the issue is each of these are individual kind of. If you want to do all of these together, the complications increase quite a bit. So each of these kept in a modular way is easier for the compiler to be written. Can you guess how many lines of code a typical compiler, say GCC, will have? Few millions of lines of code, right? Few millions, not hundreds, not tens, not thousands, millions of lines of code. Now, if you want to do big chunk of it all together, it's a serious software engineering issue. That's the reason we do it modularly, but we keep some heuristics in mind. Okay. Before I stop, I want to show if I have an example. Let me see that says where I cannot do fusion. No. Rahul. Here, maybe let's see if this has. Yeah, let's look at this one. Let's look at two things. Here what's happening, A sub 1 depends on B sub 1. After A sub 1 has been computed, I will use after A sub 1 has been computed using B sub 1, I am computing B sub 1 that uses old value of A sub 0. What will happen if you fuse it? I want you to think two things. If it is A minus 1, what will happen? If it is A plus 1, what will happen? So, but we have to go for lunch soon. But think, if I fuse these two, I have two scenarios. Scenario 1, this is A sub I minus 1. Scenario 2, it is A sub I plus 1. Okay. If possible, keep it in your mind. Close your eyes. Do you see the code in front of your eyes when you close it? Just these two. Then we can go for lunch. Think about it in your lunch. We'll come back and discuss. Madam says lunch is ready. We don't want to keep the lunch pending. He's smart. He just took a picture. Okay.